Hey guys, welcome back for another chemistry lesson. In this video, we are going to talk about the wave behavior of electrons. Up until this point, we've talked about electrons as particles, but it's not that simple. So, Louis de Broglie, I wish I knew how to pronounce his name, I'm sorry, the Debye guy, he proposed that particles could have wave-like character to them. So not just like a particle, but also like a wave. And he predicted that the wavelength of a particle was inversely proportional to its momentum. And because it's so small, the wave character of an electron is very significant. And because, like you as a person are so big, comparatively speaking, your wave character is infinitely tiny, right? So here is the equation that he used to talk about those two things together. So, if electrons were particles, we could expect them to behave like this. So, think about if I had tennis balls and I had this wall that had these two slits in it. The only way the tennis balls are going to get through this wall is by going straight here, and you're going to get like this straight like mirror image of those slits again on the other wall where they hit, right? Just like here, we've got these bright spots here and here that indicate where the electrons hit because they're particles. They're going to act like particles, right? So this is what we expected for the behavior of electrons, right? We thought they would come through here, travel in a straight line, go there. And so on the detecting plate, film, whatever it was they used, they expected to have two bright spots. However, that's not what happened. What they actually got was what we call an interference pattern, where we've got some bright lines, and we've got some dimmer lines, and then we've got some dark spaces where there was destructive interference, we'll say. And this shows that they behave like waves. We can do this exact same experiment with water and see like the waves and how they appear on this like where we see the results, right? So this experiment confused people. So when you try to observe the wave nature of an electron, you can't observe its particle nature. When you try to observe its particle nature, you can't observe the wave nature. So this is where the idea of Schrodinger's cat came from. If you know about Schrodinger's cat, it's like you have a cat in a box and it's got a vial of poison and you don't know if the cat is dead or alive if you're not looking into the box, right? It could be dead, it could be alive, we don't know. That's kind of what electrons are. That's where this idea came from. Because until I look at it, I don't see which one I'm looking at, if that makes sense. So, wave nature gives us an interference pattern. Particle nature gives us a position, which tells us which slit it's passing through, either left slit or right slit. All right, so these two properties are complementary properties. As you know more about one, you know less about the other. So let's think about trajectory versus probability. Classical trajectory in physics is just like, I launch a thing, it does a little woo, and then it lands, right? So classical trajectory of a baseball pitch, for example. Here's the pitcher, he throws it, lands in the catcher's glove. Shoop, there it goes. However, because quantum mechanics is more complicated than that, this is what quantum mechanical distribution looks like, right? So if the starting point is here and the ending point is here, there are lots of, routes we could go to and lots of not quite starting in the same place, not quite ending in the same place. And so this is where we get the sort of fuzzy S orbital model of the atom looking thing, where it's fuzzy but it's dark in the center and sort of lightens up on the way out. This is what we're talking about. It's the quantum mechanical probability distribution map. So in the case of a baseball pitch, we've got this high concentration in the middle, lower concentration further out. All right, so when we're talking about electron energy and position are complementary, and we use the kinetic energy formula for this. Kinetic energy is equal to 1/2 times the mass times the velocity squared. But the thing is, for an electron with a given energy, the best we can do is describe a region in the atom of high probability of finding it. We can't say the electron is here. We can say, well, it's probably here. There, it's probably here. No guarantees though, right? So many of the properties of the atom are related to the energy of the electron, which again, best it can do is give us a probability of where it's at. So Schrodinger's equation is this wave function equation that calculates the probability of finding an electron with a particular amount of energy in a particular place. And so there are many wave functions that could be produced, and what we do is if we look at distance versus the wave function, then that represents our orbital. That's where we get the idea of where our electrons are within the atom. So calculations show that size, shape, and orientation in space of an orbital are determined to be 3 integer terms in the wave function. And so we include the quantized energy of the electron and all of that stuff in this whole consideration. But the things that contribute to this are our quantum numbers, which I mention in another video. I will, throw it in the cards there. So we have our quantum numbers that describe the location of the electron. They all contribute to this probability of where the electron is at. They are the principal quantum number, n, the angular momentum quantum number, L, and the magnetic quantum number, m sub L.